Okay, welcome back. So in this video, we are going to look at the gradient-based optimization, specifically the steepest descent or the gradient descent optimization algorithm. Okay, so now we saw that in the context of linear regression, we were looking at this error function or the mean squared error. Which we write down and use different color, is some summation over all the data points, your y hat that you predicted using your x and your weights, and this is your ground truth or the training example y. Again, y and y hat are scalars, the squared error. Okay, so this we want to find the minimize this function. I want to minimize this with respect to w. W or the weights or the parameters of the model. Okay, so all machine learning algorithms will involve some optimization like this. This is called an optimization problem, and the idea is now we have to keep adjusting w. So adjust w till we reach minimum. Okay, of MSE. Okay. So there are many systematic ways of doing this, and they fall under this category called optimization. And there's there's a specific topic of optimization called convex optimization, but in general we won't talk about that. We'll just talk about how one would go about estimating w using this gradient descent formulation, especially in the context of linear regression. Okay, so if we let's consider some function f of x. Okay, so this is a single variable. Say f of x is our function. Okay, and we are trying to minimize or maximize this function, and we want to find out the x that minimizes or maximizes this function. We'll just say minimizes at this point. Okay, not to get confused. X that minimizes f of x. This is what we want to find out. This is what we want to estimate. Okay, so given this, how do you go about doing that? Correct. So that's the question. So for every function, like say we are going to write this as y equal to f of x. For every function where in this case x and y are real numbers, there is a derivative x. So f of x, let's say, is a smooth function, which doesn't have discontinuities. We assume that its derivative exists. So the derivative of this function is denoted as f prime of x, which is dy by dx. Okay, these are two ways of denoting this. Okay. Now we know that for if x is we are looking at single variables, and we know that the derivative dy by dx or f prime of x gives the slope, is the slope of the function f of x at x. Okay. That's the slope of the function. That's what we, and you should all be familiar with this concept of the slope of the function. Okay. So what is that? What is the slope of a function tell you? It tells you how much f changes if you change x by a small amount. Okay. So that's the idea. Or in other, the model that you are trying to that you are formulating is f of x plus epsilon, where epsilon is a very small number, would be approximated by f of x plus epsilon times f prime of x. Okay. So it's basically the rate of change with respect to x. Okay, it's locally how fast it changes when you change x. So for small changes in x epsilon, this is an approximation to this is how you calculate f of x plus epsilon. Okay, so which means that it's useful for minimizing the function, because what this derivative tells you is that how to change x in order to change f of x. Okay, now let's just look at a very simple function that we can draw, and we can appreciate how this works. So let's say we can look at f of x equal to x square over 2, and so f prime of x, the derivative is just x. So now if we draw this, 1 second. Okay. right? So just the best approximation we can draw, okay, something of that sort. Okay, so basically at x equal to 0, right, for this function f prime of x is basically 0, right? If you put f prime of x equal to x and it's at 0, so when the gradient or the derivative for this function is set to 0, it's at a critical point or at an optimal point. In this case, it's the global minimum. Okay, so for negative values of x, okay, this is negative values of x and this is positive values of x. This is x and this is f of x, of course. For negative values of x, right, we can calculate f prime of x and it will turn out that f prime of x for negative values of x will be less than 0 for x negative, and f prime of x would be greater than 0 for x positive. Okay, so we can, it's because you just have to plug in value here. So f prime of x is just x. So for negative values of x, our negative gradient gradient value is negative. For positive value of x, gradient is positive. Okay, so what that tells you is that even f prime of x is less than 0, which it means that when on this side, when f prime of x is less than 0, on this side f prime of x is greater than 0, means that we can move, by moving to the right, we can move, by moving to the right, we can decrease the value of f of x. And since on the right hand side, when x is positive, f prime of x is greater than 0, we can decrease f by moving leftward. In the sense, we move in the direction opposite to that indicated by the gradient, correct? So because the gradient is, in this case, is negative, so as we go in this direction, gradient gets more and more negative. So we move in the opposite direction, which in order to minimize f of x. Okay, so this is the gradient descent technique. So basically, the way to reduce the value of the function with respect to, or optimize the function with respect to its variables, independent variables x, is to move in a direction opposite, which is opposite in sign of the derivative. Okay, so and we can take very small steps so that we don't overshoot the optimum. Okay, so this is the principle behind the gradient descent algorithm. Okay, now we are just going to see how it works for functions which have multiple variables as input. So in our case, our last function we saw was basically a function of the weights, and there are multiple weights, right? Because we have lots of features, each feature is multiplied by a weight in linear regression, and there is also a bias term. So the number of features plus 1 basically, and in that scenario, how do we formulate this problem? So in the one-dimensional case, all you have to do is move in, find out the sign of the gradient and move in the direction which is opposite to the move in the sense, make small steps in x with the opposite sign of the derivative. Okay, so that's how we reduce f of x or minimize f of x. Okay, so this is for one dimension. So what if we have multiple variables which have multiple inputs, right? So for instance, our j of w, which we had. Okay, j of w is our last function. So we have summation over m y hat x w minus y squared. So this is 1 over m. So this is our j of w, right? This is the function. This is our last function. So the inputs, this is like if we have n features, we have n plus 1 weights. Okay, multiple inputs. So in this case, you have to be familiar with the concept of a partial derivative. Okay, so for instance, if we'll use x, but it will be confusing, so I'll just move to w's. So for instance, if you calculate in this case j of w, instead of f of x, we'll just use j of w. So delta j by delta wi, where I is the subscript for the each of the weights. Basically, this tells you how j changes only with respect to this particular variable wi. Okay. So then we can do this for every w. So delta j by delta w1, delta w2, all the way to delta j by delta wn or n plus 1. Okay, which you have a bias term. Okay, so this forms a vector. So this vector. Okay. So this is a gradient vector. What we have. So for functions with multiple inputs, so basically our function j takes a Rn vector and gives R. So it takes a bunch of features as input and produces a scalar output. Right? That's what linear regression does. Okay. So that in that case, what we want to do is take the gradient rather than the derivative. The gradient is of course the vector of the partial derivatives with respect to each of the input variables or the variables involved in the function, right? So in this scenario, how does gradient descent look like? Okay. So then in what direction should we go? So for instance, in one dimension, it is very simple. Okay. You find out the sign of the derivative and move in the take steps in the direction in the opposite sign. Okay. Okay, that's not 1D in 1D, but this is in multiple directions. So because there are infinite possibilities, in what direction do you take the step? Correct? When I say take the step, in how much, for instance, this x is fixed. So in this case, we are trying to estimate w. So we have to change all these w's, right? We have n plus 1 w's. So how do we change w? So we want to estimate this delta w, so that we can do w plus delta w, so that j is minimized. Okay. So how do we estimate that delta w and what direction do we take the step in? Okay. Okay. So for functions like our last function or the error function we are talking about, the MSE, mean square error, where j of w, this has multiple inputs, right? W's basically. Remember that x is fixed. So even though I have written it as part of the function, whenever I write g of w, x is fixed. The only thing that variable is w. So then the idea is now how do we know the direction of the gradient, right? So for instance, in one dimensional we just did df by dx, correct? So when we did df by dx, what we did which is we called it as f prime of x, we just defined that to be this way, right? Is f of x plus epsilon is f of x plus epsilon f prime of x, correct? This is the way to do it. So now if we are going to do it this way, so for multiple inputs, right? So in this case, x, I'm just switching back and forth between x and w. So please put up with me. In this case, when I use the small x, it is just some variable, okay, in one dimensions. So now how do we take, when we have multiple inputs, so w is a vector, right? W is a vector. Then in this case, how do we take this derivative? Okay, so the idea is now we want to take something called the directional derivative. How do we take directional derivative? And we want to take it in a particular direction u. So u is a vector, it is a unit vector, which means its magnitude is 1, right? U is a unit vector. Right, its magnitude is 1. And we want to estimate the slope of the function j, here j, this function j along u. Okay. So how would you do that? So the in vector notation, right? So the gradient of, let me erase and rewrite. So this gradient with respect to w, j of w, right? This is a mean square error. So we want the gradient with, we saw that this was a vector, correct? This is a vector with so many components as the size of w, and we want to take, so we will just put a vector arrow here, and we want to take a component of this vector along the unit vector u. So you just have to do u dot, just a dot product, okay? So if you want a unit vector along some unit vector, if you want your estimate a slope, especially in if it has in a multi-dimensional input, then this is the way to do it. And in matrix notation, this reduces to u transpose gradient w jw, correct? Okay. So it's a dot product between two vectors, and you can write it this way. Okay. So now, in order to minimize our j, we would like to find the direction in which j decreases the fastest. Okay. So the idea is to find direction in which j decreases the fastest. Okay, that's the thing. Okay, so how do we estimate this direction, right? So let's say it's not too hard. So we want to minimize this particular expression, right? So what do we want to minimize? We want to minimize u transpose gradient wjw. Okay, and we want to minimize this expression with respect to u, right? U is the direction we want to estimate. Of course, we know that u transpose u equal to 1 because its magnitude is 1. Okay, and the dot product, we can always write. So if you have dot product of two vectors, right? If you have two vectors a dot b, we know it's just a b cosine theta, right? Modulus of b cosine theta. It's a scalar quantity, right? So in this case also we can write in this particular notation we are using. So minimize with respect to u transpose u equal to 1. We can write this as modulus of u, not modulus the norm, right? The length of u times the length of the gradient vector wjw, right, times cosine theta. Okay. So when is this maximum? Because we want to find the direction in which f would decrease the fastest, right? So in this case, theta is the angle between u and the gradient of j. And then of course we know this is a unit vector, so we can set this to be 1. Okay. And since this does not depend on u, is independent of u, right? This particular expression here, I'm just going to, this expression is independent of u. So now we just have to find out independent of u. So now we just are left with pretty much cosine theta. So which means that we are pretty much writing something like minimum with respect to u cosine theta. Okay. This is minimized when the angle between u and gradient of j is 180 degrees, right? So that is basically when u points in the direction opposite to that of the gradient. Okay. So so in which case, which is meaning that the gradient points in the direction in which the function is increasing, and the negative of the gradient points directly in the direction where the function is decreasing. Okay. So then we can, which means that, it's minimizing is when cosine theta is -1 is right, then theta is 180 degrees, which tells you that u should be the direction opposite to the gradient. Okay. Which means that we can decrease j by moving in the direction of the negative gradient. This is known as the method of steepest descent. So this is which implies theta, or which makes cosine theta equal to -1, which means that that u and gradient of j with respect to w are pointing in opposite directions. Right, and then this gradient of j, and then the way to decrease the j with respect to w by stepping in a direction of the negative gradient. So decrease j by stepping in the direction of negative gradient. Okay. All right. So this is called the method of steepest descent or gradient descent. And the formula is the following. So w prime, the new w is your 1 second, is your old W plus minus, sorry, you have to move in the opposite direction, epsilon gradient of W, J of W. Okay? Where this epsilon is called the learning rate. Okay, again, this notation might be different. Some people might use just, we have already used lambda, so I'm refraining from using lambda. So people can use beta or some other alphabet. Okay, so this is basically a positive scalar. No, epsilon is a positive scalar. Epsilon is a positive scalar. Some number, which basically it's your step size. It constrains how big a step you can take. But this is also a hyperparameter. So we talked about hyperparameters. This is a hyperparameter, and it's one of those things that you would optimize in most machine learning algorithms. Okay. So we calculate this gradient numerically, and in many cases, and then we keep moving. And then of course remember that say W prime is W minus JW. This is one step. The second step, this would be the new W, and then you would continue doing this iteratively, and then you stop once you don't change, or W does not change appreciatively much, or W does not change in a very by large amount. So you have to fix that threshold also. Okay. So there are also many tricks associated with it. We won't go into detail because this is a very well established literature. A lot of variations of this algorithm is available in many software packages. You just have to know how to use them, but this is the underlying principle. Generally, you calculate the gradient of the function, and then you would point it would point uphill, basically in the way function is increasing. If you want to decrease the function, you just move in the opposite direction. Now this might look slightly difficult to comprehend why this happens, but if you one way of understanding this, is using the 1D example. Okay, so if just plot some x square, calculate the value of or some function in 1D, and then you calculate the values of the derivative and see in which direction, and look at its sign, and based on that you can understand which way you have to move in order to arrive at the minimum of that function. Now this is all assuming that of course I'm just making an assumption that this is all as a global minima, right? There are also functions with multiple optimum, right? Some of them could be maxima. Even at the maximum, gradient goes to 0, but it's kind of unstable. But still, you might get stuck there. You might have to climb that. And then there are these in the case of neural networks, etc. They might have multiple minima, right? So usually you have to start off with some W, with some guess of W, and from there you have to refine your W, right? And this again is you can treat this like a hyperparameter. You can start off from different values of W, but then there are all these algorithms which try to compensate for that. This is like you start off with any arbitrary W will get you there to a local optimum. So in many machine learning algorithms, especially neural networks, W generally converges to a local optimum. It's only for so-called convex functions. There's only one true optima, and that happens to be the global optimum or the global minimum. Okay, so this is gradient descent. Okay, now what we want to do for real-time learning is we want to do something called stochastic gradient descent. We'll just briefly look at what stochastic gradient descent does. But then before we go any further, this is epsilon. When we do this, this step, this gradient of W, JW, right? If you think about this is evaluated over all the training data. Okay, so this is something, because your loss function J of W, I'm going to rewrite this. Sorry, let me just rewrite this. So this J of W, if you remember, is summation over all your data sets, right? All m data points. So y hat, I'm just going to write W minus y squared, right? So now what we are trying to, what you will get here is some average gradient, right, over all these data points. That's what we will get when you do this this expression, right? In fact, in this case, you can actually directly calculate the gradient, right? If you take the derivative with respect to W, you should be able to calculate it. But we won't get into that here. But the idea is, For gradient descent, you will consider all the data at one time. Okay, and then we are actually using the average gradient here kind of to take the step. Okay, so if you have a very large data set, you have to use all those points to calculate this one step every time. Okay, so that's why even this form of gradient descent is probably not suitable when you have real time data or when you have very large data sets. Okay, so we will look at a variation of this called stochastic gradient descent, and I think a mini batch gradient descent. Okay, and sometimes I think this method is also referred to as batch gradient descent. So we will be looking at this mini batch gradient descent and stochastic gradient descent. Okay, so we were talking about the previous slide we said, if you look at the gradient with respect to W, JW, for M data sets, then it's actually the average. In this case, you just compute this as an average, right? 1 to M. The gradient with respect to W is J of your individual, your Xi's, okay, and your Yi's, your targets, and your W. Okay. Now, as M becomes very large, you know that you have to do this for every data point. So as the training set becomes big, in many cases this training set can run into hundreds of millions or even maybe billions of examples. Then this becomes computationally much harder to do. Okay. So the stochastic gradient descent is the go-to algorithm. Here, instead of doing this for the entire data set, what is done is to actually consider a so-called mini batch of examples, right? So this is like the understanding. This is the following. So here I said, no, you're kind of doing an average, or ideally, you should call this the expectation, but we will just work with averages. Okay, so you are calculating empirically, you are approximating the expectation with an average, right? For this particular case. Now we have a very large number of samples. So what this so-called mini batch stochastic gradient does is, so for every calculating a step size, we don't have to estimate this average on the entire data, but rather a sample of the data. So we do an average of the sample and use that to update the weights of your linear model. Okay. So the mini batch size, which is M prime as we call it, which is a subset of M, is chosen to be a generally small number, right? It can be anywhere between usually powers of 2, sometimes 132, 64, 100, something like that. But you will have tens of thousands of examples, but you might just use a mini batch of 50 to 100 to for every step. Okay, so that this is you choose these 100 randomly, right? And you can use that, and in fact the cost to compute to a step, given that you fix that M prime, right? So the mini batch size is M prime, which is a very small number. Okay, it remains the same regardless of how large your data set is, right? So then, but you can continue to take steps at the same cost no matter how large your data is, right? So then the gradient estimate, right, which we call, which is basically, if you want to call gradient in this case, is some 1 over M prime, some small number, the gradient with respect to W, and this is again I equal to 1 to M prime. This is your loss function J of for individual data points. Okay. So once you have this gradient estimate, mini batch gradient estimate, then you can use your usual W goes to, and I'm going to just put a giant tilde here to and W goes to W minus epsilon gradient estimate, your mini batch gradient estimate, right? So that's your stochastic gradient descent. Okay. Surprisingly works very well for a wide variety of problems. Okay, optimization problems. In fact, a lot of the deep learning techniques that we will see in the next over the next couple of weeks, they all use this algorithm for estimating the weights of their models or the parameters of the model. Okay, and not only for linear regression but for a wide variety of algorithms. And it's it's a workhorse of modern machine learning techniques. Okay, so again, we're not going to look at consider how whether it will converge, what are the what are the samples, theoretical analysis, etc. Just to understand the basis on which we we use these algorithms. This is good.